Plus after these, right?
Yeah, I'm gonna go to. I'm sure 5:30, but other than that, I'm just gonna like go.
Physics hard.
It's not hard so far, but I feel like it's because we're learning not too hard stuff. But like, I feel like it's gonna be good.
Have you took physics at high school?
It's my first time, so I think it will.
I have to take the next semester.
You did, and your reflect was 2.
Yeah.
So you'll be, are you gonna do the calculus 3 at the same time?
Maybe or not.
Well, that's what I'm doing right now, but. I feel like it's helping me because we're learning like the same things in physics and.
It's one of those ones. Just. Get my help through. It's like.
Yeah. But,
So.
I have come. But not by forcing. Like when she was first.
Your efforts shall not be. All right, it's 4 o'clock. Let's go ahead and get started. How's good afternoon, everyone. How's everyone doing? We're already at mid-semester form in terms of attendance right now. Looking good. All right. So the plan for today is we're going to continue with our lecture on constrained optimization. So last time, we covered the technique of direct substitution. That's probably the most practical technique for solving these problems. But we're going to learn a bit more of a traditional method today called Lagrange multipliers. So we started a little bit on Tuesday, but today, we're going to dive more deeply into it, do a couple of examples, and then hopefully finish up this section on equality constraints, just so that next Tuesday we can start on inequality constraints. Okay, I think that's all the announcements I have. Are there any questions I can answer before we get started for today? Okay, all right, let's go ahead and get started. Okay, so the topic, well, let me scroll over first, actually, because we kind of started it last time. Okay. So the method that we're going to be learning today is called Lagrange multipliers, right? And so this is kind of the last thing that we talked about last time. So the idea behind the Lagrange multipliers method is to take all of your equality constraints, put them in standard form. So if you put them in standard form, they all equal 0, and then add them directly into your objective function. Okay, and so the idea is to form this quantity here, known as the Lagrange function, which is simply the summation of your original objective function f together with the summation of all the equality constraints, right? So on the far right-hand side there, I have a summation, notation there. Just to account for the fact that, you may have problems that have multiple equality constraints. Most of the time, for the problems that you guys are gonna do, you guys are only gonna have one equality constraint, so, that would just be one additional term. Okay. All right, and so of course, the crux of this whole thing is this addition of this new variable here, lambda, and so we call this lambda the Lagrange multiplier. And if you look at the structure of how I've kind of labeled this this new Lagrange function, you can see that, our new Lagrange function is now going to be a function of these Lagrange multipliers as well. Okay. And so essentially we're kind of modifying our problem here to kind of add additional design variables to account for the constraints. Okay. Now that might seem like a really bad thing, right? So we've talked a lot in this class about how, just adding design variables to a problem will make it harder to solve. And that's still true. And so, the problems that we're going to solve with Lagrange multipliers are going to have more design variables than before, right? And so at first you might think, we're going backwards relative to our direct substitution method. But these Lagrange multipliers are they're not true design variables in the sense that, they're not going to be part of our design. They're more kind of like just a mathematical tool that we use in order to help us solve these. Okay. Okay. Let's go ahead and pick it up from there. Okay. So just like I mentioned, so the Lagrange function that we form is going to depend both on the design variables as well as our new Lagrange multipliers that we have. So just a reminder too that, the amount of Lagrange multipliers that you add is going to depend on how many constraints that you have. Okay? So there's going to be one Lagrange multiplier for each constraint. And so with that in mind, once we've formed our Lagrange function, we can then solve it kind of in our traditional way. Okay. And so we would then from here proceed to take the first order partial derivative, set them all equal to 0, and then use that to solve for the optimal values. And whatever value that you get from the variables from that system, that's going to be either a max or a min, or worst case it's going to be a. Okay. So that's all there is to it, you know, the only thing that's really new is just adding these Lagrange multiplier terms. But besides that, you know, we're still kind of following the same method as before. All right, any questions on this before we jump into an example? Okay, so let's do an example just so you can see how this all comes together. Okay. So let's consider a two-dimensional optimization. So our two design variables in this case are going to be x and y. Okay. Let's say that this is equal to 5 times x, or excuse me, 5 over x times y squared. Okay. So that's our objective function. Right, so this objective function is going to be subject to the following constraint. And so the following constraint is that x squared plus y squared is equal to . So whatever value, whatever optimal values that we get for x and y, they have to follow this this constraint. Okay. And if you kind of recognize this formula here, that's the formula for a circle in the xy plane. Right. So whatever optimal result that we find must sit on that circle of radius 2 in the Cartesian plane. Okay, and so what we want to do, let's compute . Let's compute optimal values for x and y . From this problem. We're going to use the Lagrange model. Okay. So to use the Lagrange multiplier method, we need to form our Lagrange function, right? So we need to take our objective function and add it to add to that all of our constraints. But before we do that, we need to put our constraints into standard form. So first step. Let's put our constraint into standard form. So standard form is just, there has to be a 0 on one side of the equation. So let's take our constraint and subtract 4 from both sides. So then our constraint is x squared plus y squared minus 4 equals to 0. That is our constraint g of x and y in standard form. Step number 2 is to take this and then form our Lagrange function. So our Lagrange function in this case, we have one constraint, so that means we're going to have one Lagrange multiplier. So our Lagrange function is going to be a function of 3 variables, x and y, which are our original design variables, and our new Lagrange multiplier lambda. Okay, so this is what we have. So we have our original objective function plus lambda times g. So let's plug in. So we know f of x and y in this case is 5 divided by x y squared. And our constraint here is lambda times quantity x squared plus y squared minus 4. And that is our Lagrange function. just our original objective function, plus lambda times the constraint. All right, step three. Step three is we're going to take our first order partial derivative of this. So we're going to take the first order partial derivatives and then set them equal to 0. Okay. So we're going to have three derivatives to take in this case. And so we have the derivative of L with respect to X, the derivative of L with respect to Y, and the derivative of L with respect to lambda. Okay, first we have partial L, partial X. Okay. So I'm going to take that partial derivative and distribute it to each of the terms here. Remember, differentiation is a linear operator, so that means when we have terms separated by a plus or a minus, we can just distribute the derivative to each one of those individually. Okay, so let's take the derivative of this, and so the derivative of this is we're going to get a minus 5 over x squared y squared, okay, plus derivative of this we have 2 times x times that's going to be equal to 0. Okay, next we're going to take the partial derivative with respect to y. So same thing, I'm going to distribute that that y derivative to each term individually and then take their derivative. Okay, so let's evaluate this, and so this is going to give us a minus 10 divided by x y cubed. Okay. Because we get a minus 2 that comes out by taking the derivative of y raised to the minus 2 power, that multiplied by the 5 on top will give us minus 10, and then we reduce the power of y by 1. So we get xy cubed on top. Meanwhile, this term here looks very similar. So this is going to be 2 lambda . Okay. And then finally, we need to take the derivative of L with respect to again, I'm going to distribute that lambda derivative all throughout. Partial lambda 1d5 over xy squared plus that lambda looks like an egg right there. Plus partial lambda of lambda times x squared y squared plus y squared plus minus 4. Okay, so this is probably the simplest derivative that we have here because the first term does not depend on lambda at all. And so taking the derivative of that first term with respect to lambda is just going to make it go away. Okay. And then the second term is linear with respect to lambda, right? And so all we get from taking the derivative with respect to lambda is just our original constraint and standard form. So this is x squared plus y squared 4, not equals to 0. Okay. And so that's actually pretty, you should get that, right? And so the Lagrange multiplier method is designed in such a way such that, when you do form your system of equations afterwards, your constraint is one of the equations, right? And so if we look at these three equations here. So the three results that we have. So what we're gonna do is we're gonna solve these three equations. Value for x, a value for y, and a value for lambda. All right, so we have a system of three equations and three unknowns. All right, any questions on this so far? Okay. All right, so once you kind of get to this point, generally what I recommend is that you solve for the design variables first, right? It's not every time that you need to solve for the Lagrange multiplier. Sometimes you do, and in fact, that can actually be really useful in some cases. But generally, it's better to solve for the design variables first. Let's do that. Okay, so let's solve for the values of the design variables, okay? And so if we don't really care about the value for lambda at this point, let's try to eliminate it from our equations. Right, so if we can eliminate lambda from the equations, then all we're left with is just a system of two equations for our two unknowns. Okay? And so the only, believe it or not, the only equations that have lambda in it are the derivative that don't actually take the derivative with respect to lambda. Or maybe that's not surprising, right? By taking the derivative with respect to lambda, you kind of get rid of it from the equation. Okay, so I'm going to focus on the first two equations first. And in fact, if we kind of look at these carefully, the second term in each of these equations look very similar to each other. It's 2 times lambda times something. Okay, so let's solve for 2 lambda from the first two equations. Look at the first equation. What I'm going to do is I'm going to add the plus 5 x squared y squared to the other side of the equation. Okay, we have 2x lambda is equal to 5 over x squared y squared. Okay, so this is from equation 1. The derivative of the Lagrange function with respect to x. Let's take this equation and let's isolate 2 lambda on the other side. So let's divide both sides by x. That's going to get rid of that. And then on this side, we have an additional x in the denominator. And so we get 2 lambda is equal to 5 over x cubed y squared. All right, so let's do the same thing with equation 2. Okay, so for equation 2, let me come back up here. Okay, equation 2 is what we got by taking the derivative of the Lagrange function with respect to y. Okay, so once again, I have that minus 10 over x y cubed. So let's move that to the other side of the equal sign. We have 2y or 2y lambda, excuse me, is equal to 10 over x y cubed. Okay. Once again, I want to isolate 2 lambda on that side just because it's a common factor between the two equations. I'm going to divide both sides by y. So what we get from that is 2 lambda is equal to 10 over x y to the fourth. All right. So this is great because if we look at what we have for equation one, what we have for equation two, they both have values for 2 lambda, right? And so if both of those things equal to 2 lambda, then those two things must equal each other. We have 2 lambda is equal to 5 over x cubed y squared, which is equal to 10 over x y to the fourth, which is equal to 2 lambda, right? Everything here is equal to each other because of you know, they're tied together by the factor of 2 lambda. Okay, and so of course, you know, we only really care about what's in the middle. The whole reason we're doing this is to eliminate lambda from the equations. And so we have that relationship 5 over x cubed y squared is equal to 10 over x y to the fourth. Any questions on how we got to this point here? Okay, good. All right, so now if we take this equation, so if this becomes our new kind of combined equation between 1 and 2, and then we combine this with our constraint, we have the 2 equations that we need to solve for, you know, solve for this system. Okay, so let's simplify this a little bit. Because eventually what we're going to do is we're going to plug this into our constraint. Okay. All right, so let's so you know and everything you know that I did up here with setting it equal to 2 lambda, that's just kind of you know algebraic strategy, I guess that's what I like to call it. So you know, if you solve equations differently, then that's you know, that's fine too. Okay. But for me personally, you know, when I see things in fractions like this, I don't like fractions, and so I try to kind of multiply things through to try to minimize that or limit it as much as possible. So I'm going to take this y to the fourth because I know that's the stronger, that's the term with the higher exponent. I'm going to multiply it by both sides, and so I'm going to bring it up top here. Okay. And I'm going to do the same thing for the x cubed. So the x cubed I know is a higher power than the x on the other side. So I'm going to multiply both sides by x cubed. That should eliminate the x on the bottom. Okay, so doing that, we get 5 times quantity y to the fourth divided by y squared equal to 10 times quantity x cubed divided by x. This, of course, simplifies really nicely for us. And so if we cancel out the powers, we get 5y squared is equal to 10x squared. And in fact, you know, we can divide both sides by 5. So we divide both sides by 5, we get y squared is equal to 2x squared. Really nice, kind of elegant solutions. This. So you might be wondering, you know, why am I leaving it in terms of squares, right? So I mean, technically, if you wanted to get an equation, you should take the square root, and you would be right. But the reason I'm leaving it in the squared form is because I know that our constraint has x squared and y squared. So this just kind of makes this a bit more convenient for us. Okay. Okay, so let's come back to our constraint equation. so our constraint equation is x squared plus y squared minus 4 is equal to 0. That's what we got by taking the partial derivative with respect to lambda, but it is still just our original constraint. Okay. Okay, so let's plug in for y squared. So from this equation, we know that y squared has to equal 2x squared. So we get x squared plus 2x squared minus 4 is equal to 0. Let's simplify this. Let's move the minus 4 over to the other side. And so we get 3x squared is equal to positive 4. And then from here is just simple arithmetic. So we're going to divide by 3, take the square root. So we do that, we get x is equal to square root 4 over. All right. So that's good. Okay. And then finally, what we need to do is we need to plug this back into our circled equation up here, solve for y squared. And so we know that y squared is equal to 2x squared. And so that tells us that y squared equal to 8 over 3. Yes.
Are we ignoring the negative for the square root?
Yeah. So we're just taking the positive.
Okay.
Yeah, I don't say it all the time, but oh, actually that I need to go over something for the homework too. I'll cover that at the end. But for most problems, I kind of make the implicit assumption that I'm only looking at positive values. I should be explicit. I should kind of say that in the problem that you should only be looking for positive values. But you know, if I don't say it, then it's kind of implied. That's relevant for 2E of the homework, because there was a minimum that I kind of missed because I only looked on the positive side of the x-axis. Okay, so we got y squared is equal to 8 over 3. So let's take the square root. And so we get y is equal to square root of 8 over 3. Of course, you could simplify that. You can technically simplify the x1 above that too. You can factor out the square root of 4 to get a 2 out in front, but you know, this is perfectly acceptable. All right, and so that's you know, we solved a constraint optimization problem using Lagrange multipliers, right? So for this problem, you know, we didn't really do anything with the Lagrange multiplier, and so it kind of just ended up being direct substitution with extra steps. But having that Lagrange multiplier, we are going to do something with that in the next example. So you know, it is a little bit more of a general. All right, any questions on this? Okay, good. All right. So now that we have the basic idea of Lagrange multipliers, you know, let's see kind of what else we can kind of do with this frame. All right. First thing I want to talk about is you know, even though we found an optimal point here, we don't know if this point is a max or a min, right? Remember, that was kind of an important part of our classical methods technique. The unfortunate thing is that our technique for declassifying these optimums is either, you know, max or min, changes a little bit because our Lagrange function is different than our objective. Because normally, you know, in the classical methods, for multi-dimensional problems, we computed our Hessian matrix, right? Unfortunately, you know, we have to do a little bit more work now because we're adding these Lagrange multipliers to our problem. And so this official matrix doesn't officially have a name. But for our purposes, you know, I like to call it the augmented Hessian matrix. And so it's nicer in some ways in that, you know, you only have to compute one number. You don't have to go through the whole principal submatrices thing. The downside is that it's usually a pretty big matrix. So you have to compute the determinant of a kind of a big thing. Okay. So let's see. So the matrix that we need to get the determinant of looks like the following. So we're going to take the determinant. It's going to be of this kind of big matrix. Let me do this. Let me do it. Let me show this matrix for a you know, two-dimensional problem with one constraint. And so that's going to end up giving us a 3 by 3 matrix here. Okay, so in the top left corner, we have L11 minus Z. And at that point, we have L12, and I'll define what all these are in a second. I mean, if I actually make this smaller. All right. And then in the bottom right, we're gonna have a 0. And then everywhere else, we're gonna have these derivatives here. G1, two, one. Okay. All right, so let's label all of these. So all these L terms, all the L terms are those are our typical kind of second order partial derivatives of our Lagrange function. So L11, for instance, would be partial squared L partial x1 squared. Okay. L12 would be the cross terms. We have partial squared L partial x1 partial x2. And of course, L22 will be second order partial derivative of our Lagrange function with respect to the second design variable, partial x2. Okay. So it's partial squared L over partial x2 squared. Okay, and then what are the G's? And so the G's here are the derivatives, first order derivative of our constraints with respect to the design variables. Okay, so G11 equal to partial G partial x1. Okay. And G12 is the same as G21. That's partial G partial x2. Okay. And then in the bottom right, 0 was just 0. So that's kind of the nice thing about this this matrix here. Okay. Okay. And so we need to take the determinant of this matrix. And what's different about this matrix, you know, obviously, you know, we have the constraints. And so the constraints are now kind of built into our Hessian matrix. Okay. But another new addition here is the addition of these Z terms on the diagonals. And so those z terms are actually undetermined variables at this point. So by taking the determinant. By taking the determinant of this matrix, we're going to end up with a polynomial in terms of z. And of course, we have a polynomial. We can then solve for the roots of that polynomial. Okay. And depending on the sign of the roots of that polynomial, that'll tell us whether our optimum is either a max, a min, or neither. Okay. So these are the rules for this. Okay. I know I'm going through this very quickly, but you know, I'm gonna demonstrate this in the next example so you can kind of see how this all works. So this is a lot of information. And in fact, you know, anything that involves the Hessian matrix is always kind of a lot. So I would say for now, just kind of write this all down and then, you know, you'll kind of see it in action in the next example. Okay. So if all the z's are positive, if all the z values are positive, then we have a basically a positive definite matrix. Okay. Then our optimum is a minimum. If all the z values are negative, if all the z values are negative, then our matrix is negative definite, and so that means we have a maximum. If you have z values that are some are positive, some are negative, and so there's not a clear kind of they didn't pick a side, then we have neither. And usually when you don't have a max or min, but your derivatives are zero, then we call that a saddle. Okay. All right, so in summary, you know, the way to kind of classify whether you have a max or a min using the Lagrange multiplier method, you need to form this augmented Hessian. And then depending on the values of these z's that come out of that calculation, you can then classify it as a max, a min, or a saddle. Don't worry, you'll see all of this in the next example. It looks like a lot, but you know, once you do one, it becomes clear. Yeah.
For the z values you're talking about, you mean the roots of the z?
Yeah, exactly. Yeah,
Got
the roots of that problem. Any questions on this before we jump into an example? Okay, all right, so let's do an example. This one is a little bit more fun than our first example. We're diving back into geometry. And so, we're gonna be looking for geometric dimensions in this case, okay? So in this example, we want to find the dimensions of a tube or a cylinder. And the main dimension that we're going to be looking at is just the radius of the cylinder as well as its length. So we know already off the bat that we have a two-dimensional optimization, two design variables, okay? And so just like the example we did on Tuesday, we want to maximize the volume of the cylinder. So we need a constraint in this case, and so if you just want to just want to say give me the maximum volume cylinder, you just say a cylinder with infinite radius and infinite length, right? So we need to constrain this in some way. Our constraint in this case is going to be on the surface area of the cylinder itself. And so we want to find the maximum volume of a cylinder if the surface area is constrained to have a value of 24 pi. A little bit of a different problem here than our previous one, but still quite the same. All right, one situation that you can think of this is that say that you have a limited amount of wrapping paper and you want to give you want to see what's the largest volume gift that you can give to someone if it were cylindrical in shape, right? And so the amount of wrapping paper that you have is exactly 24 pi for some reason that maybe Michael sells it in that capacity, and you want to try to find the biggest gift that you can wrap. Okay, so let me go ahead and draw a cylinder just for visualization. And so the length of the cylinder, L, and the radius of the cylinder, go ahead and call that big R. Okay. All right. Any questions on the setup for the problem? Okay. All right, so in this case, we're given just a word problem, and so we're not explicitly given the mathematical forms of the objective function or the constraint. So let's do that first. So step one, let's formulate. Let's formulate our objective function and constraints. Okay. Sometimes plural. In this case, you only have one, but to be general, you might have more than one constraint. All right, so let's start with the objective function. So the objective function we know, or our objective in this optimization is to maximize the volume, right? And so that means our objective function should be the volume of the cylinder. All right, so we have F, our two design variables in this case are R and L. Volume of the cylinder is just the area of the caps, and so the area of the cap is pi r squared. And then we're going to multiply that by the length. Okay. Our constraint in this case is the surface area. So let's come up with an equation for the surface area first, okay? And so the surface area of a cylinder has two components. And so we have the surface area of the lateral part, okay? But we also need to account for the surface area of the caps as well. Okay. So let's come up with the surface area of the lateral part first. Okay. And so the lateral surface, you know, the way that I kind of best visualize this is actually as a piece of wrapping paper, right? And so if you were to kind of take the outer shell of a cylinder and kind of unroll it, right, you would actually kind of have a rectangular sheet in that case, right? And the dimensions of that rectangular sheet, on one side you have the perimeter of the cap. So that's 2 pi r. So 2 pi r is the perimeter of the circle on the caps. Okay. And then you're going to multiply it by the length of the cylinder. So that's the surface area of just the lateral side. But we also need the surface area of the caps as well. And there's two of them. So we have multiplied by 2. And then the surface area of the caps is just the area of a circle. And so that's the total surface area of our cylinder. All right, so according to the problem, this is going to be constrained to a value of 24 pi. All right, so let's simplify this. Let's get rid of some of the parentheses. We can go ahead and put this in standard form too, because we're going to need to do that if we're going to use our Lagrange multiplier technique. Okay. And so our constraint, and we'll call it G of R and L, is equal to 2 pi L plus 2 pi R squared minus 24. So that's the two components that we need to move forward. So we have our objective function. Our objective function is just the volume of the cylinder, and then our constraint in this case is the surface area, which must equal 24 pi. Okay. All right. Any questions on how we got here? Okay. All right. So now that we have the objective function, we have the constraints. We're now ready to form our Lagrange function. All right, so a Lagrange function, member, is just going to be the summation of our objective function, our original objective function, as well as our constraints. Okay, we only have one constraint in this case. And so our objective function L. Oh, I guess I had a poor choice of variable names. I forgot we're going this direction. Okay, so our Lagrange function is going to be a function of our two design variables, the radius and the length of the tube. Okay. I know there's two L's. I should have chosen a lowercase L for the length of the cylinder. But we're stuck with it, so let's just go on and move forward. And then we also have our Lagrange multiplier as well. Okay, so let's add those together. So we have pi r squared L. That's our original objective function plus lambda multiplied by our constraint, which is 2 pi L plus 2 pi r squared minus 24. All right, so now that we have our Lagrange function, we're just going to go through the same process we did last time. So let's go ahead and take our first order derivatives. Let's take our first order derivatives and set them equal to 0. So just like the last example, we have 3 derivatives to take in this case. So first, let's take the derivative with respect to the radius. Okay. And so this is going to give us 2 pi L plus lambda times 2 pi L plus 4 pi R. So just like the first example, what I did was I took that derivative with respect to R, distributed to each of the terms in the expression there, and then took their derivative. Okay. Luckily, everything here is just either a linear term in the variable or it's a quadratic term, and so taking the derivative is straightforward. Okay. Again, you just have to be careful because these are partial derivatives. Okay. Next thing we're going to do, we're going to take the partial derivative of the Lagrange function with respect to the length. Okay. So because of my poor decisions, you know, we have a kind of a strange looking partial derivative thing, partial L. But that's the partial derivative of the Lagrange function with respect to the length. All right, so let's go ahead and carry out this derivative. We have pi big R squared plus lambda times quantity 2 pi R. And that's it. Equal to. All right. And then finally, let's take the derivative of the Lagrange function with respect to the Lagrange multiplier. Okay. So we're going to take partial L, partial lambda. And doing so, all that we're going to get back in this case is just going to be our constraint. And so we do that, we get 2 pi L plus 2 pi R squared. Or excuse me, there's an R squared here. Minus 24 pi equal to 0. There's not an option there. All right, so now we have a system of 3 equations that we need to solve for our 3 unknowns. Okay. And so you may go about this in any way that you please. Okay. I'm going to follow a similar strategy that we followed for the first example. So I'm going to eliminate lambda from the first 2 equations and then solve for the values of R and L from. All right, any questions on how we got to this point here? Okay, all right, so let's go ahead and proceed. All right, so we'll solve the first 2 equations for lambda and then set them equal. Okay, so I'm going to start with equation 1. And so equation one, that is our partial derivative of our Lagrange function with respect to the radius. Okay. So I'm going to isolate the lambda term on the other side, on one side of the equation. Okay. So I'm going to move this 2 pi RL over to the other side. And so doing so, we get lambda times 2 pi L plus 4 pi R is equal to minus 2 pi RL. Let's solve this equation from lambda. So I'm going to divide both sides by the terms in parentheses. So we get lambda is equal to minus 2 pi RL divided by 2 pi L plus 4 pi R. Okay. Let's do the same thing with equation two. So equation two, I'm gonna isolate lambda by itself once again. So equation two, once again, I'm gonna take this pi r squared, move it to the other side of the equation. So isolate lambda on one side. Okay. We have lambda times 2 pi r is equal to minus pi r squared. And I'm going to divide by 2 pi r. That is lambda is equal to minus pi r squared divided by 2 pi. All right. So now that we have both of these expressions here, so both of these expressions are equal to lambda. So let's go ahead and set them equal to each other. And then thus we're going to eliminate lambda from the equation. And actually, I guess before we do that, there's a lot of canceling that we can do. But let's cancel it all at once. Okay. And so if we set these two equal to each other, we get a minus 2 pi r times L divided by 2 pi L plus 4 pi r is equal to minus pi r squared divided by 2 pi. Okay. All right. So we have an equation here where a ton of the terms are going to cancel. So this is going to be very satisfying for people who are into that stuff. So first thing we should notice is that we have pi's everywhere. So all the pi's here are going to cancel out with each other. That's good. Next thing we notice is we have factors of 2 everywhere as well on the left-hand side. So we have this 2. We have this 2, and we have a 4 here. So if we factor out 2 from the top and bottom, the 2's are going to cancel out. And then this 4 is going to become a 2. Next thing we notice is that on the right-hand side, we have an r squared up top and an r on the bottom. So of course, those are going to cancel out. And finally, the last thing we can cancel out are the negatives. So we have a negative on this side, negative on that side. We're just going to Hopefully that was very satisfying to cancel out all that stuff. Because now we have something that's quite simple. And so on the left-hand side here, we have R times L divided by L plus 2R. And on the right-hand side, we just have R over 2. Oh, in fact, we can cancel out one more thing. We have an R on both sides, so let's go ahead and cancel that. I missed one. Okay. And so the final one we have L divided by L plus 2R equal to 1/2. Right. So we're almost there, at least for this part here. Remember, we want to get an equation where we can plug into our constraint, right? So let's work on this a bit more so we can get an explicit expression for either L or R. Okay, so what I'm going to do is I'm going to cross multiply here. So I'm going to bring this L plus 2R, I'm going to bring it up top here. And this 2, and bring it up top here. Okay. And so that's going to give us 2L is equal to L plus 2R. Let's subtract an L from both sides. And so subtracting an L from both sides gives us L is equal to 2R. Okay. So all that work for a relatively simple expression, but this is actually really interesting, right? Because if you think of everything that we've done up to this point, we haven't actually touched our constraint yet, right? We've only just worked on the objective function. Think about it, right? And so this result right here basically says that, if you have any cylinder and you want to maximize its volume, right? That means the length must be twice the size of the radius. So that goes for any size cylinder. And so in theory, if you specify the radius, so let's say that you're limited, the maximum radius that you can apply is maybe 10 centimeters. That means if you want to have a cylinder with maximum volume, you set the length to be 20 centimeters. Okay. So that's a really cool result, even without kind of incorporating our constraint. But of course, we do have some hard numbers here, so we do have a limitation on the surface area. So let's go ahead and accomplish it. So our constraint was given by the equation partial L partial lambda. So let me go ahead and remind you what that is down here. So that expression was 2 pi r squared plus 2 pi r L minus 24 I equals 0. Okay. Let's plug in for L here. Okay, and then that's going to give us one equation for us to solve for the radius. Okay, so luckily L only shows up once in this equation, so L only shows up right here. Let's go ahead and plug in for that right there. And so we have 2 pi r squared plus 2 pi times r times L, which we know is 2r. And so that's going to give us a 4 pi r squared I'm gonna go ahead and move the 24 pi over to the other side, just because I know where that, I know that it needs to be there. So all of this is equal to 24 pi. All of the pi's are gonna cancel out, so let's go ahead and cancel out all of those guys. The two r squared and the 4r squared are gonna combine on the other side and become 6r squared. That's equal to 24. Okay. And then from here, it's pretty straightforward, so let's divide both sides by 6. 24 divided by 6 is 4. And so we take the square root. Yeah, the radius has to equal 2. Okay. 2 what? I don't know. I didn't have the foresight to put units on that surface area. So that surface area was 24 pi meters squared, and this would be 2 meters. Okay. All right, so let's go ahead and plug this back in. Right, so now that we have a hard answer for the radius, we can then now compute the hard answer for L. Okay. And so doing so, L has to equal 4. All right, any questions on how we got to this result here? Okay. All right, one more thing that we'll do. I think we'll stop there after that. Let's actually plug these back in and solve for lambda. Okay, so let's take these and solve for the Lagrange multiplier value. So you can use either of the equations. So to go back up here, you know, you can use either of these two equations to solve for the value of lambda. Okay, I'm going to use this one just because it's a little bit simpler. Okay, and so based on that equation up there, we know that lambda has to equal to minus I r squared divided by 2 pi r. We know that the pi's are going to cancel. R's are going to cancel. Okay. We know lambda is equal to minus r over 2. So let's go ahead and plug in our value for r. So we know r in this case is 2. So from this problem, we get a Lagrange multiplier value of minus 1. Okay, so before we wrap up for today, you know, there's still a bit more to this example. You know, first of all, we have to kind of confirm that this is a maximum. Although very similarly to the last one, you know, we can kind of intuitively guess that this is already maxima, because it doesn't make sense for this to be a minimum. Because if you wanted a cylinder with 0 volume, that's as low as you can go. And so, you know, the fact that we got a non-trivial answer means that this must be a maximum. But you know, we'll go through the calculation to confirm that. We say next time. We're going to confirm this as a maxima using the augmented Hessian matrix. For this one, it's not too bad just because, everything again is kind of linear or quadratic terms. And so when you take the second order derivatives, you end up with just a lot of constant terms. Okay. But we'll do that next time. Second thing we're going to do is we're going to look at this Lagrange multiplier value. So we got a Lagrange multiplier value of -1. And that is significant actually. And so the most notable case is that, we got a negative sign for a Lagrange multiplier. And so next time we'll have a discussion of, what does it mean to have a negative Lagrange multiplier? What if your Lagrange multiplier is positive? Is it possible to get a Lagrange multiplier of 0? So what does that mean? Okay. And to kind of like, to kind of put the thought in your head, over the weekend, with regards to that question too, I want you guys to think about, so for this problem, we did it with a very specific value of the surface area, right? So I told you the surface area was 24 pi. So what would happen if we made that constraint either more restrictive? So let's say that we reduce the maximum allowable surface area. So let's say we made it 16 pi instead. Or what if we increased it? I want you to think about, what happens if we change the value of the constraint. Okay. Right, and so what we'll talk about on Tuesday is that this is the main benefit of doing the Lagrange multiplier approach. And so, in a lot of ways, it just kind of ends up being direct substitution with extra steps. Well, that extra steps actually gives you some interesting information about your design problem in general. Okay. And a lot of times, when you're running an optimization problem, you're not just interested in the optimal values, but it's also useful to understand some information about your system just in general. So how does your system respond to changes in the constraints? How does your system respond to changes in the design variables? Okay? And so what you'll see is that, as we kind of get through the class, we learn different algorithms that kind of give us different information. We'll actually be able to learn some really interesting information about our systems. And so, that's kind of another area of optimization of kind of understanding your system a bit better through running these kinds of tests, running these kinds of algorithms. All right, any final questions on this before we wrap it up for the week? Okay, all right, so that's all we got time for. So thank you guys for coming out today. We'll pick this up on Tuesday. So hope you guys have a good rest of your day. Hope you guys get to weekend. I will see you next week.
Thank you.
What? No lab. I noticed the way you talk about like. So I don't get. Yeah, it's really. Yeah, I don't get.